I will say that of the part 2 material, today is the driest. It's the farthest back in time we're going to go. It's the most different. It deals with oceans and continental land masses we don't have today, so it's kind of hard to wrap your head around. So I really want you to think about it as you take away the lessons from today. What are just the key points, the basics? Don't get lost in the minutia. Just focus on the key large-scale details. All right, so part 2 then. We're going to answer the question in this part over the next 3 weeks, let's say. How did the Southeastern landscape that we all see, how did it form and over what time scales? Specifically, let's take a look at some of the kinds of questions that I want you guys to help me think about. Number 1, when did the first basement rocks get put down? Raise your hand if you ever heard that term, basement rock. Key in geology, I'm sure basement rocks are pretty well thought of and talked about. Basically, what it means here is, you've got bedrock, right? You can go out here to Rotary Park and see outcrops of limestone or chert. And then you can go down and you could go through the various layers. This is Mississippian rock. You can go down and you can hit, Devonian shale and Silurian limestone and Ordovician limestone below that. If you're to dig down about 200 or 300 feet, you go through those periods of rock. But what's below the Ordovician, which is the rock that you see at Nashville? What comes before Ordovician? Anybody? You guys really got to start? No, it's higher. What's lower than Ordovician? You got to start making sure you guys come back in knowing these periods and eras and epochs, okay? Cambrian, right. So Cambrian, what's before Cambrian? Precambrian, right. So we can go back, and Precambrian is a long span of time. But we can go back in eventually till we hit a granite base rock. We don't have any igneous rock here at the surface. But underneath us, you can go down far enough to where you can hit the original granitic igneous rock from when North America first formed as a continent. And that's called basement rock. And so it's down there. You might have to go 1,000 feet to hit basement rock. I don't know the exact depth to be sure. You know the depth? But the depth to basement here is not that deep. I mean, it's down there, but it's not that deep.
Or we talked about how all the tectonic plates walk on big continents.
Yeah.
Are all basement rocks granitic igneous?
That's right. Yeah. Everywhere. And so those are all the original cores of each continent. Who knows what that term is called? I don't know if we talked about it yet or not in class. The core granitic foundation of every continent. It has a term. All right. It's called, Ian, do you know it? Starts with a C. R. It's called a craton. So the cratons or the cratons are the core foundational rocks of each continent. So Australia has a craton. Europe has one. For example, have you ever thought, well, why are Europe and Asia considered to be separate continents? I mean, they're fused after all, right? Is it? Anybody ever thought that other than me? Well, the reason is they're fused today, but they weren't fused, 400 million years ago. They were separate continental land masses, each of which had their own core assemblage of basement rocks or its own craton. Same thing for India and Madagascar. That's why we call India a subcontinent, right? It's really a continent, a continental landmass. It happens to be small, but it fused in with Asia on the south side. So today we call it part of Asia. So it's similar. I mean, it's not 100%, but those have their own craton bedrocks is the part I'm trying to emphasize. When did those first get established? We're going to talk about that today. Another core question is, when did the mountains around us form? When did the Ouachitas form and the Appalachians form? And there may not be an exact point in time. There may be multiple points in time. how do we get that modern coastline, that very distinctive coastline that comes over with the Gulf of Mexico and Florida dipping down? There's a time and place when that happened. We can trace exactly back to, and I want you guys to have an understanding of how that happened. What sediments contributed to the formation of the continental shelf? Take a look here. The continental shelf, right, is before the ocean drops off into the deeper ocean, into sort of these abyssal zones. There's a shallow continental shelf around all sides, for example, of Florida. It's not that way on every landmass. I mean, you can step off the western coast of South America into an oceanic trench that's 10,000, 12,000 feet deep. But here we don't have that. We have a continental shelf right along our coast. Well, that's important because during the ice ages, when sea levels dropped, what do you think happened to the state of Florida? It got a lot bigger, right? There would have been pronghorn antelopes racing across these coastal plains that today is underwater, and there's instead a continental shelf there. There would have been mammoths and mastodons, and very likely there would have also been people inhabiting some of these areas before global sea levels rose. Chase?
I would say, yeah, I think it's about, you know, they've always made a bunch of theories on how
Yeah.
America's, one of the ones that was like science theory was
Mhm.
that also believe folks seal hunters were going along fishers and possibly hit that.
Absolutely.
And then
Exactly. Yeah, the coastal corridor hypothesis is still very much alive and well. Yeah, and there's a big raging debate among archaeologists and paleoanthropologists about, you know, did first people come in through the land bridge, or did they come by the coastal route? We'll talk about that when we get into the human history portion of this class for sure. And what is the age of the Nashville Basin? If you go back just a couple, you could see the Nashville Basin right there. You know, when did that form? Well, we're going to talk about that a little bit. Why is the Mississippi River where it is? There's a very clear reason why the river flows right down the heart of the country. What do you mean that Florida used to be part of Africa? Well, it did, and we're going to talk about why that is. The northern part of Florida is Africa. It is geologically part of the African crust that got dislodged when Africa rammed into North America and became isolated and fragmented and sort of glued on to the eastern coast of America. So yeah, the foundation bedrocks over northern Florida is Africa. We'll talk about why that happened. And how do we know that a large chunk of central North Carolina was once an island in the Atlantic Ocean? Well, hold your horses. We're going to get to all that. Okay. And speaking of the Atlantic Ocean, how old is it? And what was its role in things like the Gulf Stream? Why is that important to us here? There's talk in the last couple of weeks that, you know, in coming decades or centuries, probably not centuries, but in coming decades, the Gulf Stream current might get shut down. If that happens, it would be detrimental to humans. Now, it could just be, you know, hyperbole, and it could be scare tactics, but it also has happened in the past. And global ocean currents do change, and they cause major worldwide ramifications.
The reason why the UK is even.
Oh, yeah. I mean, you know, UK would be habitable in the sense that it'd be like Quebec, northern Quebec, or the Northwest Territories. You know, the city of Yellowknife, Northwest Territories, it's habitable, but it's also near the Arctic Circle, right? Now, would London be a flourishing metropolis, and would you be able to grow palm trees in the southwestern cities of England? No, absolutely not. What keeps London and the rest of England and Scotland and Ireland and northern France with an equitable climate that is such a large population is the very fact that you have this warm body of water that brings it warmth all throughout the year. Yeah. And if that gets shut down, they're so far north that they'll become very cold, like parts of Russia or parts of Canada. Say again?
Serves them right.
Serves them right. All right, well, I don't know about that, but why does all this matter to biologists or to ecologists, right? Why do we care about these high-level questions? Let me get your thoughts on that for just a few minutes. Let's discuss, why do we care about some of these big questions that I've just posed to you? Because I have to do this because I don't want you guys in the midst of this 3-week-long journey we're about to take to start looking at me with glazed over eyes, like, what in the hell am I doing in here? What's this guy talking about rocks still for? It matters. Why does it matter to you, Brandon?
So, just personally, actually, going back to about my Vanderbilt thing.
Yeah.
Whenever I was looking for advisors, I was looking in the biology department. And nobody in the biology department was looking at things I wanted to look at, which is ecology. I had to go to the earth sciences department. And I didn't realize why the only ecologist at Vanderbilt was in the earth sciences department. So I actually asked when I went there, I was like, I would have like never found it if I didn't accidentally stumble across the department. And the chair and me were talking, he was like, well, when you think about ecology, which is like the overall grand scheme of things, you know, you're looking at very broad concepts. You're not just looking at the organisms, you're looking at the biomes that they live in. And a lot of that ties into, ecology ties into earth science.
Right.
And how things form, in turn how the organisms form and adapted to how the geology is and the biogeography and all that stuff. So to me, you know, going into a career where I'm going to look at these big broad concepts, I'm going to need to know, you know, not just the organisms. Again, and I've told you like why I'm taking this class, but how their habitats form and why they evolved for that habitat.
And what group are you going to be studying at Vanderbilt?
Well, I'm actually studying jaguars.
Oh,
Yeah, as I'm going to do my study species. Down
super,
in
man.
the Pentanol.
Oh,
Yeah,
man, that's great.
yeah.
Best of luck to you, man.
Wetland jaguars and the movement.
It's amazing. Let's talk sometime. I'd like to talk to you more about that.
Dr. Haas asked me if I needed a tech. I'm taking out.
All right. Yeah, we should talk about that. That'd be cool. Can I work for you? I'm just kidding. All right. What other reasons? Why does it matter? Why we know where the Mississippi, why it's flowing where it is with the continental shelf and all this stuff? Just a couple more responses. Anybody?
For me, it's kind of been a lifelong passion project to map out the evolutionary history of life as we know it. Evolution is subject to the forces of geology and the physical environment around it. Like anything as simple as like an allopatric speciation event where a mountain pops up can have huge consequences that trickle down to hundreds of millions of years. So you're talking about memorizing epochs a second ago. I know that material, but only in the context of mass extinction going on with what was alive and dying at the time. So trying to learn it backwards from what was happening to the rocks and therefore what happened to it feels strange to me, but it is important to know because it's hugely shaping the biological factors that we have.
I'm just appreciating the artwork on your arms here. You got the DNA molecule, right? You got some bugs here. Super. That's awesome. Well, yeah. You know, how many times have you seen someone give a seminar, right? Either here or at another university, and they present a phylogenetic tree, right? And they say, here's how these plants split apart. But then when you ask those people how to explain the real world geological, ecological, climatic, geographical variables that led to the patterns on their phylogenetic tree, I guarantee you 9 times out of 10, they go, oh, I don't know. This is just what the genes say. You know, this clade is sister to this clade. I know that clade's sister to that clade. Well, but they split apart, you see, during the Miocene. Well, when was the Miocene? I think it was 2 million years ago. Wrong. Get your numbers straight, right? Most of them can do good to that point, though, even if they get the Miocene right. But then you ask them, what forces during the Miocene were promoting this segregation, this split, this vicariance event between two species? You know, most of them can't then go into and say, oh, it's because there was a mountain range that uplifted, or it was because there was a rain shadow that formed east of the Rocky Mountains, and it split the forest into two giant halves, you know, or the timing and the why behind it. And I'm not casting, you know, any kind of negativity because it takes a tremendous amount of knowledge to build that up, right? And I don't have a lot of that detailed genetic knowledge, but it's a reminder that we gotta also tell the other part of the story, and we gotta talk about rocks and soil and, you know, that stuff because it informs so much. And I don't want you guys to get out of here without having had very good exposure to it. All right, let's get to it, okay? Why does it all matter? We talked about. I want to introduce you a cool website. There's probably a more modern version of this, which I need to update. This is called the Paleo Map Project. This is, if you go to scoteasy.com, is a pretty cool site. I'm going to just kind of hit the highlights on this a little bit, assuming it's still active. Yeah, it is. Let's take a look. We're going to explore the Paleo Map Project together. First of all, if you've been here before, raise your hand if you've ever seen this. Notice here on the left side, you can see the different periods of Earth history. So Precambrian, Cambrian, Ordovician, Silurian, etc., all the way down into the epochs of the modern day. We got Eocene, Miocene, etc. And what I want to do is just kind of show you. Let's take a look at, for example, the early Carboniferous, which contains the rocks when Clarksville was formed, for example. You can see the configuration of the continents here. And here's South America, here's Africa. So what's really neat about this is you could just sort of go back and forth through the course of time and look at these different periods. I would encourage you to explore this. There's also a climate history tab here, and there's an animations tab. Let's see if this animations will work here. Now, this is a really old website, and I'm probably going to have to try to find a new version. But used to, back in the day, you could actually see an animation that would pop up, and you could drag across it. Apparently, the animations feature on this is not working. So I'm gonna jump out of this, and we're going to keep going. But I do want you to at least know about this website because it's important to being able to look at the different periods of Earth history. Okay, let me pull this back up here. All right, so now one of the first things we want to do is sort of talk about some of the, again, what built America? What built the United States? What processes led to that? Because I took so much time there, I'm going to ask each of you to sort of redirect your attention. You know, stretch it out, you know, move those arms around. Act like you're shadow boxing. I need everybody to be on your best attention. Maybe stand up, kind of walk around a little bit, get yourself fired up. Scratch your head. I'm going to take a swig off my drink. And then we're going to get going. It's kind of hot in here. Everybody hot? Man, it's pretty warm. All right. I think I'll be okay, but it is getting kind of hot. Ken, you hot? He's good. All right. The word that we're going to start with is orogenies, mountain building, right? If we think about the mountain building processes, the orogenies that led to the Appalachians, we don't just have one process, one mountain building event. In fact, we don't have just two. I've given you two here. We have multiple. We have at least two, but probably more like four, and you'll become familiar with those. Now, I would encourage you, I'm not going to go into them here, but I would encourage you to go into these links and watch these on YouTube so you can see these animated videos that show the processes of these mountain building activities for what's called the Grenville orogeny. That's the earliest one that created part of the Appalachians that we know of today. And then the Alleghanian orogeny is the more recent one, but really the Alleghanian is more like three put together. So if we're talking about the basic construction of the North American continent, going all the way back down to the foundation, you know, down to the bedrock, the basement rock, then what we could see is that we have rocks that span anywhere from 1.1 billion years. For example, underneath the eastern part of North America here. And these are what we call the 1.1 billion year old Grenville rocks. They are part of what's called the Grenville orogeny, the Grenville mountain building episode. But then there are other older time period rocks, so 1.3 to 1.6 billion years across parts of between California and underneath Kansas, for example. And if you go farther north still into parts of, say, Utah and Colorado or North Dakota, South Dakota, the rocks are 1.6 to 1.9 billion years old. All the way up until some of the oldest rocks around are part of what's called this Canadian Shield region of Canada, around Lake Superior and Minnesota. And those rocks are our oldest ones in North America at 2.5 to 3.4 billion years old. All of these rocks are types of granites. So there's a big family of rocks, you know, granitic rocks, true granite and gabbro and rhyolite and just all kinds of different rocks that form, that are igneous rocks that form. Notice how these rocks sort of aggregate together, right? You can imagine that these oldest areas of the oldest parts of the Canadian Shield were formed first. And then these other parts sort of got aggregated onto it, okay? These other formations. And we're going to specifically dive in on the Grenville rocks to see how the rocks of our region and of Eastern North America were added to that.
How did these regions get there? Some of them are regular old English.
Right.
There's Yavapai, Mazatzel, whatever language that is, and one is slave.
Yeah.
What's going on here?
Right. Slave in this case probably refers to the Great Slave Lake of Alaska, of Canada. And I have no idea about how that name came to be.
Sure.
I suspect it's probably not connected to slavery as we think about it, but I don't know. Yeah, I don't know. And then the Yavapai Mazatau, I have no idea. You'd have to ask a true geologist, not one that plays in the movies, right?
Am I gonna have to spell that on a test?
No, no. All I want you to know is Grenville rock. So let's talk about the Grenville orogeny. Well, number one, the Grenville orogeny, and just say a word with me one more time, orogeny. And what is an orogeny? It's a mountain building event, right? So we expect then that the Grenville mountain building process led to some mountains at some point in time. And in fact, geologists have been able to reconstruct where the Grenville Mountains were roughly 1 billion years ago. They were a high mountain range that actually stretched across the world. In this case, here in North America, the Grenville Mountains, though, primarily are found across Eastern North America, down into parts of northern Mexico and central Mexico. And then also notice that a little bit of Grenville rocks shown in this inset are in places like northern Scotland today. That wasn't the end of the Grenville Mountains, though. If we look at this next slide, and we could put those two places in perspective. Here, for example, is North America under its old paleogeography name of Laurentia. You do need to know the name of Laurentia. Later, you're going to need to know the continent called Euramerica. But for right now, just know that Laurentia is the ancestor of modern-day North America. How do we know that? Well, it's sort of turned. Normally, we think about North America as north and south. In this case, it's turned completely 90 degrees from what you would expect. This is the Hudson Bay of Canada. Here's most of what is today's Alaska. And then right through here, you can't see it because it's not there yet. But Florida, eventually, about 500 million years later, will come in right here and be added. And this would be Florida, about where that arrow is. So Laurentia is the old name for the ancestor continent of North America. I want to go ahead and throw one more ancestral continent at you called Baltica. And that is the ancestral continent that is today's Europe, particularly parts of Western Europe. Notice that Siberia is its own continent at this time. Amazonia, which is parts of the Amazon region of South America. West Africa is a separate continent from the Congo. from India, from Arabia, and Australia. Notice then, all the continents are in different configurations. Also, we are in the southern hemisphere at this point. So not only are the continents different names, they're in different rotations, different configurations, at different places in the hemisphere. Things are very different. Most people would never have guessed, for example, that North America, as it is today, was so closely approximated with Antarctica or with Congo or West Africa. Now, where was Scotland at this point? It was right up here on the northwest side of Baltica. And here's Greenland, for example. So the Grenville Mountains then was this area all in this dark coloration right through here, especially right in this zone. All the continental land masses were coming together. That's why the Grenville Mountains runs through those areas today. So you can see then they form what's called the basement rock. Now, in addition to these rocks, which formed roughly 1 billion years ago, there's only a few places today where you can actually see them at the surface. And that's because in most cases, like under Nashville, for example, they're buried under 1,000 or more feet of rock, of other kinds of younger rocks. But these areas that you see here, in 3 places show where you could see the Grenville rocks still exposed if you wanted to go see them. Okay? So these are billion-year-old rocks. One place you could go is northeastern Tennessee and southwest Virginia, North Carolina, kind of up around the region we call the Amphibolite Mountains ecoregion, around Boone, North Carolina. That's a place. Now, those existing mountains are not necessarily the Grenville Mountains. They have rocks that are part of the Grenville Mountains, okay? The old Grenville Mountains, they rose up 1 billion years ago, and then they eroded completely. So whatever you see that's left over, oftentimes are nearly flat, or those mountains were lifted up again in a later mountain building episode. Does that make sense? Here's another bit of Grenville Mountain rock. This is in southern Virginia, right on the Virginia-North Carolina border. And this is the type of rock formation called the Picture Creek Diabase, which is a type of granite found just north of Raleigh, North Carolina. This is a very flat plain. It's part of the Piedmont region. But those rocks are from the Grenville orogeny, from the Grenville time. And then finally, right down here on this place called the Pine Mountain Window, where Georgia and Alabama come together, you'll see that little area there. And this is called Pine Mountain. And here we have Grenville age rocks that are present in parts of this very low mountain range here. Here's a photo of a geologist from your textbook who is studying 1.2 billion year old Grenville age rocks. These are granitic rocks here. It's part of the Pine Mountain Formation. Now, granite, naturally, and igneous rocks, one of the minerals that's included in granite is a mineral called zircon. And it's also part of an element, the element zirconium, which is a type of metal. Zircon is highly durable. It lasts for, hundreds of millions of years. In fact, zircon can last over 1 billion years. Because zircons can survive geologic processes like erosion and transport, flowing down through a river, high-grade metamorphism, like being squashed under a mountain range, for example, then they contain a very rich and varied record of geological processes. Zircon, which weathers away from granite rock, though it weathers away as these crystals, which can be carried away, and they're oftentimes part of various rock formations, igneous rock formations, sedimentary rock formations, metamorphic rock formations. So geologists can go into sandstone, for example, or this metamorphosed sandstone like quartzite, and there are zircon crystals in this rock in Alabama near Birmingham that has zircon crystals which were formed way older than this rock itself. So the Hollis quartzite formed about 300 or 400 million years ago as Pangea was forming. But the actual zircon crystals that sort of got caught up in that quartzite are billion-year-old zircon crystals from the formation of the Grenville Mountains. So even though the Grenvilles rose and weathered away, their crystals still remain because they got reconstituted in the younger rocks that were forming along different places.
When geologists are looking for, are they measuring like the size and abundance of the crystals to gather information, or are they looking at impurities that get trapped in the crystal structure?
They're looking at, so you can do things like age. You can use these to do radiometric dating using uranium and molybdenum isotopes. These are the kinds of minerals that you need to look at when you want to date the oldest fossils in the world. If you need to get radiometric date, so carbon dating, for example, is only good back to 50,000 years. If you want to date the first prokaryote fossils from Western Australia at 4.4 billion or 3.6 billion years old, you got to go to zircon crystals to be able to get the kinds of isotopic radiometric dating capable of going back that far, because they have these very long half-lives of the elements and the minerals that help make up these crystals. And there's lots of applications for these that are far beyond my knowledge base, but that's just one. But they are highly durable, and from that, you can get some pretty extreme information. So again, these zircon crystals, maybe they originated in the Grenville Mountains when that mountain range was running through Australia and South America and Amazonia, right, and the Congo. So what does that enable you to do? No matter what continent you're on in the world, you should be able to look at these zircon crystals and date them and say, yeah, these zircon crystals originated from this ancient Grenville Mountain system. Although today it's in Alabama, right? It's one form of evidence we can use to see where the Grenville Mountains were, is based on the zircon crystals and their mineral composition. So let's spend some time and talk about what was Rodinia like. I don't know that we even define that, by the way. This ancestral continent, this supercontinent, we often hear about, if I were to ask my kids who are in high school and said, kids, what do you think about, what was the world's, how many supercontinents have we had? Everybody knows Pangea, right? I mean, it's like common knowledge. It's on Saturday morning cartoons, common knowledge. The mayor of your town has heard about Pangea, right? How many of you have heard about Rodinia? Raise your hand if you've ever heard Rodinia. Okay, 3 of you. Okay, so it's the continental supercontinent that preceded Pangea. And so if you go back to Pangea is roughly 350 million years old. Rodinia is 1.2 to 0.9, so 900 billion to 1.2 billion years old. So Rodinia comes together and then breaks apart. Okay, then when those continents come back together, eventually they form Pangea, and then they break apart to where they are today. But what's going to happen in a couple 100 million years when they come back together? They'll form another supercontinent. Okay. So what was life like in Rodinia? Well, at roughly 1 billion years ago, it was a harsh, inhospitable place. Let's talk about what was not here first, okay? Let's set the scene. No plants, period. Mark them off your list, not there. No birds, no vertebrates, period, right? And really probably not even any eukaryotes to speak of. This is a prokaryote-dominated, bacteria-dominated world. So the primary things that you would experience were, in terms of organisms, were archaebacteria. That's one of the 3 domains: archaea, prokarya, and eukarya. So kind of like the archaebacteria that you would see today around the hot springs of Yellowstone National Park. The methanophiles and the halophile type bacteria that live in very salty or hot thermal vents. That's kind of what you would have expected. There's also very little to no free oxygen during this time period. So we're talking about a very poisonous atmosphere. Oxygen is not present in high amounts. Most everything that we have, there are really almost no photosynthetic life, except maybe the earliest blue-green algae, the prokaryotic algae. So almost everything at this time period are chemosynthesizers. They are not using oxygen for their metabolic pathways. They're using, other alternatives to oxygen. And then mostly a lot of organic processes are taking place. And again, not much in the way of photosynthesis at this period. We do have fossils, however, that actually predate the formation of rhodinium. If we go to Western Australia, we can see those fossils, and that's a microscopic image of the first prokaryotic, these are algae from Western Australia, thought to be cyanobacteria from this region. Now, we can begin to see the geologic evidence of the effect of those prokaryotic algae on the atmosphere, because these are photosynthetic at this point. I mean, they are beginning to photosynthesize. So when I say like, we don't have a lot of photosynthesis going on, it really means we have no plants, that whatever photosynthesis is happening in aquatic environments because of prokaryotic algae, like the blue-green cyanobacteria. So these little critters up here in the left, they are photosynthetic. They do have the precursors to chloroplasts. They are cranking out very low levels of oxygen that gradually takes, hundreds of millions of years to build up in Earth's atmosphere to give us the atmosphere that we have today. Now, as that's happening, oxygen that's building up in the atmosphere is reacting with the various rocks, the surface rocks. And some of these rocks, which are rich in iron, are oxidizing under this increased presence of oxygen. So what happens if you have an old exposed metal piece on your Jeep, for example, that's not painted? It oxidizes, it rusts. It begins to turn rusty red. Well, you can see those rusted rock layers here because they're rich in iron, and that iron is reacting with oxygen to create that it's being oxidized, and therefore that's responsible for those reddish layers. You wouldn't have that if cyanobacteria wasn't cranking out increasingly more and more oxygen in the atmosphere through photosynthesis. So we can actually see that signature in the rocks. We can begin to see the spike at which oxygen levels increase to such a point because it's preserved through these banded formations in things like chert rocks, for example. Now, the fossils that I mentioned that we could see from Western Australia, those dates about 2 to 3 billion years ago, even before the formation of rhodinium. Let's look and see what kind of formation ecosystems that those would have existed in. We would have had smaller land masses. The continents were not nearly as large as they are today. Here you can see where the land sort of meets the sea. And out in this, you would have had these colonies of bacteria called stromatolites. And these basically are these kind of mushroom-shaped domes that were common right out here in the shallow seas in 1 to 2, 3 feet of water. And this is what modern day stromatolites look like off the coast of Australia. These dome-like clusters here are colonies of cyanobacteria. They're prokaryotes. And if you were to look at those in a cross-section shape, they consist of thousands of layers that are built up over time. And you can take a look, and here are some fossils of stromatolites, these stromatolite reefs, like I showed you in this picture back here. That's a stromatolite reef right there along the coast. Here's one of Australia. This is a fossilized stromatolite reef from Alabama, from the Precambrian age Copper Ridge Dolomite Formation. So here are these chunks of stromatolites right here, these big mushroom-shaped rock fossils. But they're not really rocks at all. They are, they're fossilized stromatolites. If you were to cross-section those, Today, they are formed as chert formations, and you can see the layers in those that are those bacterial colonies. Here's now one that sort of bridges the going from Precambrian into Cambrian times. This is a Cambrian age stromatolite in Alabama. And here you can see those colonies again preserved there in Northeast Alabama. So as we go from 1 billion years, and we have this sort of very exotic sort of, bacteria-dominated ecosystem, we're going to take a couple of giant leaps forward. What I want to do now is take you up to the point of about 700 million years ago, Precambrian time frames. Take a look at what happens over the span of about 100 million years from Precambrian times, from 716 million years through 630 million years. I've said to some of you in this class before, I'm sure, that, Theo and I know have talked about this, that Tennessee has never been glaciated. Tennessee has never was covered in the glaciers that came down during the Ice Age. Those are two different statements, right? It is correct to say Tennessee was never covered with glaciers from the last Ice Age. It is not correct to say that the land that is now Tennessee was never glaciated, right? That's very different. Under one, we're saying it wasn't glaciated in the last 2.6 million years of the Pleistocene. But there is one point in Earth history we can go back to where most of this region that is now Eastern North America, in fact, most of the world was covered in glaciers, like Brazil and parts of South Africa. And that is what we call snowball Earth 700 million years ago. So if we go back, there was an enormous amount of volcanic eruptions. It was leading to these very cold conditions in the atmosphere, blocking out the sun with volcanic dust. That put us into a worldwide glaciation, except for these little bitty places around the equator that were largely free of ice, these refugia. And we stayed locked up in ice for many tens of millions of years. So take this forward from 716 million years, we finally go to a point where we get completely opposite conditions. Eventually the glaciers melt. We go into very hot conditions. It's called what's called a hothouse, almost like greenhouse conditions. But in just a few tens of millions of years' time, we go back into a global ice age again. And it's at this point that we are now shrouded in a glacier once again. Now, again, take that for what it is. We're talking about 600 to 700 million years ago that parts of this region would have been glaciated. So just make sure you know the difference there. And then, of course, once we got out of snowball Earth and we got to about 630 million years, then never again was this part of the world glaciated, ever. So we've never been glaciated except during the time we were under what's called snowball Earth. Any questions about that?
Yeah,
All right.
question.
Yeah, Laura?
When you say this part of the earth, are you talking about roughly our present day longitude, latitude? Or are you talking about our location on this continental crust?
Yeah, generally speaking, I'm talking about the southern part of North America. Has never been glaciated. Well, again, back until we were covered in snowball Earth. But, you know, if you're in Ohio or New York, you can't say that because those regions were covered both by the recent Ice Age glaciers as well as the glaciers of snowball Earth.
Gotcha.
Okay. Now here, it doesn't probably make that much of a difference, but try talking to somebody in Costa Rica, right, or Brazil, and telling them that, or in tropical West Africa, those areas were glaciated too, but you have to go back almost 700 million years before they were part of snowball Earth. All right. Now, we're going to jump ahead of that a little bit, more recent in times. We begin to go through, after around 600 million years ago, we're about to go through a mass explosion of biodiversity. My friends here who are people who study various animal groups, it sort of predates the big explosion of animal lineages that we see around 530 to 550 million years. What is that time period called? You know? Yeah, the Cambrian explosion, right? Most of the multicellular lineages that we think of today, like sponges and mollusks and all kinds of other groups, right? They all kind of originate as part of that Cambrian explosion. But just prior to that, we had this weird multicellular group of animals, organisms that were called the Ediacaran fauna that people don't know much about. This entire group is thought to have gone extinct. They were mostly marine organisms in oceans. Some of them were very much plant-like, but the Ediacaran fauna predated the Cambrian explosion. And then at about 550 million years is when we see that eruption of all those other major forms of life. Now let's take a little bit of a switch here. And I'm going to bring you now down to the Appalachian Mountains, because it's really in the rocks of the Appalachians is where we sort of break, we span, that we bridge that time period from before the Cambrian explosion through the Cambrian explosion to rocks after the explosion. Okay, what do I mean by that? A lot of these rocks, for example, over here, this is I know it's a little bit hard to see. Here's Knoxville, here's Asheville, North Carolina, here's Charlotte. A lot of these rocks that make up the Piedmont and the crystalline mountains ecoregion we've already talked about, that's all Precambrian stuff, right? Well over 1 billion years in age in some cases. But then the rocks that underlie Knoxville are Cambrian in age. And then the rocks that make up the Cumberland Plateau are even younger, like Mississippian and Pennsylvania. So part of what we're going to do as we go forward is really begin to understand how the mountain range that is now the Appalachians will get built and constructed. Now, this map is fairly complicated, and I don't want you to get scared by it. But what I want you to sort of begin to look at with me are a couple things. Number one, notice the trajectory here, or the orientation is probably a better way to say it. How is the land oriented? I know we're looking at just a block of land, but how are the mountains oriented? What direction? Yeah, northeast to southwest. That's critical because it has to do with how the continental land masses were moving into one another. Like Africa, for example, coming all the way across the Atlantic Ocean, moving into North America on its northwest. But don't forget that Baltica is over here, moving in to the west from the northeast. And remember why we said the Ouachita Mountains run east-west? What could explain that? Exactly. Whatever's happened with South America's ancestor is coming from the south, bumping into the north, creating an east-west trending mountain range. Okay. Now, there's a few other terms in here and a few other things I want to highlight. Number one, we've already been through all these ecoregions in depth. In fact, this is not even an ecoregion map. This is a map that just shows you mostly some of the different units of land. I want to call your attention to this right here, an exotic terrain. What does that mean? What is an exotic terrain? Well, go ahead, Laura.
It doesn't belong there. It's for, it's like disjunct little section.
Exactly. It's disjunct. This is a body of land that at once was not connected to the rest of North America. You remember all those, the Grenville Mountains and the Yavapai, Mazatl, and we talked about the others, right? They all seem to be just sort of joined together. Well, that's what's happening right here. This Carolina exotic terrain is exactly what it sounds like. The region of central North Carolina is exotic, meaning that it comes from somewhere else. It's a terrain, meaning a body of land, and it's largely centered over North and South Carolina. So where did it come from? It was an island in the middle of the ocean that was the ancestor before the Atlantic Ocean. And it got pushed in and sandwiched between what? Africa and Laurentia, the precursor continents of North America. So when they jammed into each other, there was an island in between that got caught up and it got pushed into and annealed, or basically sutured, onto the eastern coast of North America, which brings up another term, the Piedmont suture. That's the zone at which the Piedmont, which you've already been exposed to, connects to and gets fused with the eastern edge of the Blue Ridge Mountains. So there's a suture zone there. The final thing I want to point out here is all these red lines with these little triangles. What do those represent? What do those red lines with triangles represent? Not ridge lines. They kind of somewhat correspond to ridge lines, but not entirely. They are faults. Those are fault lines. Yeah, in some cases, they're thrust faults. Yeah, so that just shows you the huge amount of tectonic activity because of all the faulting and slipping that's happened through this region. Remember we talked about the Cumberland thrust block, this big chunk right here? That whole big massive amount got shoved over into what is now Kentucky and Virginia. All right, now I'm going to introduce this slide and we're going to take a break. This is a publication from a few years ago, Patillo et al. 1998. A few years ago, hell, it's a quarter century ago. But the purpose of this is to diagrammatically show you the relationships between North America, Africa, and this Carolina exotic terrain. So we're going to start, when we come back from break, we're going to start at 1.1 billion years ago. And by the way, the abbreviation GA means billion years ago. And here you can see Laurentia in sort of shaded here in the left, and we've got Africa. They came together to form the supercontinent Rodinia. And then what we're going to do is we're going to follow this through time and look at the opening of the Atlantic Ocean, the further opening of the Atlantic, and eventually it's going to come back around. It's going to begin to close in until we get here, where all the continents have come back together as what? Supercontinent Pangea. So this is a diagrammatic view going over the span of more than 500 million years from the Rodinia Grenville orogeny on the upper left to the late Carboniferous Permian Alleghanian orogeny, which formed in Pangea in the lower right. We're going to break this into its components and walk it through so that you'll kind of understand it better. All right, so I just basically introduced this, the graphic that you see here. These are the events leading to both the formation of Rodinia and Pangea, but there's a lot of stuff in between, right? So looking at the top left of this, that's the formation of Rodinia. That's the close of what's called the Grenville orogeny. That's when it ended, roughly 1.1 billion years ago. And you can see there on the left is Laurentia, and on the right is Africa. You guys on the screen, can y'all see that?
Yes, it
Perfect.
could be bigger, but we can see it.
Yeah, and I'm going to have a lot more of these sort of zoomed in versions you'll be able to see in a little in throughout the talk. Yeah. So we're going to go from that all the way through the opening back up, or the dismantling of the supercontinent Rodinia, which is what's happening here. And you can see there it says the nascent Iapetus Ocean, or the beginnings of the Iapetus Ocean. I know I'm throwing a lot of names at you, but that's the ancestor to the Atlantic. So before the Atlantic was there was the Iapetus Ocean. It had to open up, and then it closed in again when Pangea pushed it together. There's even another ocean in there or two called like the Theocraic, and we'll get into all that. So as Africa now is moving away, the crust is beginning to thin out. You see it sort of pulling apart in this what's called this late Proterozoic extension. That's going to continue to happen. Where again, over here is Laurentia on the far left, Africa is on the far right. And then notice that you've got a couple of land masses out there, like the Piedmont terrain, and Avalon, which is an island in the middle of the ocean. I realize this is not all very easy to see. And again, we are going to go through this in much greater detail at a finer level. Notice what's happening here is we have the ocean, and that ocean is spreading apart. Notice here the ocean comes to a little rise, and that's called the mid-oceanic crust, or excuse me, the mid-oceanic ridge. So what is actually driving the spreading of that ocean is called seafloor spreading, where that magma is pushing up right there in this entrance. And that as that rock hardens, that igneous rock is solidifying as part of the ocean crust. It forms a rock type called basalt. That basalt then spreads out a little bit. And then it continues to erupt underwater, spreading out, spreading out, spreading out. It's that spread, that ocean floor spreading, is what's pushing these continents apart. And it all starts in the middle of the ocean, those tectonic forces, okay? That's what's driving this sort of ocean, the tectonic plate activity is what's driving this, yeah.
Does the path of that ridge wander over time, or does it stay static over 700 years?
Yeah, those paths, those tectonic plates, they're shifting as things like the poles are shifting and the equatorial zone is shifting. And as continents are moving, all of these the continents are floating like an ice cube in a vat of water, right? They're floating and they're all moving together in sort of parallel and in unison. So they may be shifting a little bit across what is basically a molten liquid mantle underneath. And so they are shifting and moving all the time. The amount of movement is about equivalent to the rate at which your fingernail grows, by the way. So that opening up of the mid-oceanic ridge is happening at the same rate that your fingernails grow. So you can sort of estimate then for those to spread apart 1,000 miles, how long would that take? You could get the sense by that calculation roughly. James?
I was just wondering. It's moving around. With that affects formations.
What kind of formations?
Inlets.
Oh yeah, for sure. Definitely, you know, as you have marine life in one of these oceans, as Africa is colliding with North America, there's nowhere to go in some cases, right? And now this isn't happening instantaneously. It's happening over tens of millions of years. So some of those species, sure, they have a place to go, but those that are sedentary, they're caught up in the middle, and in many cases, we have mass extinction events, which are happening as a result of like the formation of Pangea. A lot of that extinction was in the oceans as coral reefs were going extinct, and many types of organisms were going to extinct there. All right, so anyways, I'm not going to spend a lot more time here going through this because we're going to get into nuts and bolts, but I do want you to study this diagram. And I don't necessarily want you to be an expert on it. I want you just to know how to work your way around the diagram and to make sense with it. And as I said, we'll come back and focus on this at various points in the class. So by the late Precambrian era, roughly 550 million years ago, and is when that Precambrian comes to an end. We're about to change into the Paleozoic era. We're going from the Precambrian era into the Paleozoic era. And this is really the first period, right, that I wanted you to know. I wanted you to know Cambrian, Ordovician, all the way through. So this is kind of the starting point. So if you haven't memorized those yet, well, now is really your time to pick up because we're going through it systematically, starting today from the Cambrian all the way to the Holocene. That's what the next 3 weeks of class will do for us. All right. Now, Laura, to your point, you mentioned that you couldn't see those diagrams very well. Notice what I've done up here in the top.
Perfect.
I've taken those little miniature diagram versions, and then I have zoomed in on that as it applies to this specific time period so that we can sort of see what's happening. Okay. Let's keep our eyes focused on the question in hand. The question at hand is, how did the American continent form, right? I don't want you to get lost in the minutia of, was this the ancestor of the Atlantic Ocean at this time, or was this an island? I want you to think about the American continent. That's really what we're keeping focused on. So now let's look at the American continent. After Rodinia is being pulled apart, right? Everything is being separated at this point. And notice that that's reflected right here off the eastern side of Laurentia, this continent that we call now North America. You can see in the image on the right with that double arrow, the double white arrow, is indicating the seafloor spreading that's driving those two continents apart. All right, and here's the mid-oceanic ridge that is sort of helping to drive that apart. It's actually not there. It's right there. That's the mid-oceanic ridge that's opening up those land masses. Now, as that's happening, we have rift valleys. All right, let's go back and talk about what that means. That means that a continent, once it's ripped apart, the crust is literally being ripped open. Okay. As that happens, that is when we begin to see the eastern coast of America take shape. That's when we're going to begin to see, for the first time ever, the beginnings of the Gulf of Mexico. Not the modern day Gulf of Mexico, but how the edge of the coast is, the shape of it, right? That's when we're also going to begin to see the precursor to what will eventually become the Mississippi Valley. Not the river, but the conditions that will allow the river to form. Think about that. The conditions needed for the Mississippi River to be where it is today have their origins at the time of the Cambrian explosion more than 500 million years ago. 500 million years ago is how far we go back to begin to explain where the modern day Mississippi River is. So let's look in now. I want you to focus on this edge right here. From what is East Texas up to southern Arkansas, across Alabama, Mississippi, and up through here, right? Watch how that edge changes. And we're going to dig in a little bit deeper. Here we go. This map, which is from your textbook, begins to show the Laurentian landmass up here on the upper left. You have that newly emerging ocean here. Promise me that you won't get confused yet about the terms for all these oceans, okay? Iapetus and some of the other oceans, the Phaeac Ocean. We'll sort all that stuff out. But for right now, I want you to keep focused on the landmass and what's happening on the edge of the continent. Now, what are these orange stripes here? Those are rift zones. That's where Africa, or what is not Africa, but the continent that's now off to the east, has been ripped away. Okay, and as that ripping is happening, due to that sort of splitting effect, it's creating all kinds of fault zones back here. That impact on the land, that tugging the land, is causing the continental crust of America to ripple and buckle and break into fault lines. All right. Now, remember when I showed you guys originally the Mississippi River Valley and there was like a whole bunch of fault lines? It was that first day we talked about geology. I said, what are all those lines up in Western Kentucky? And we ultimately said those are fault lines. They originate from this process between 800 and 500 million years ago. As those continents were ripping away, that's when those fault lines began to form. Now, I'm going to draw something here on the board for you. So imagine then that you've got a piece of land that very simplistically, and for those of you on the computer, my apologies, I'll turn my camera on, maybe that'll help. Yeah. So you've got sort of a horizontal line here. And imagine then that ripping action takes place. So you've got this pull effect from this direction and from that direction. Okay. And what that does, it begins to fracture or break the rock, the crust in places. Now, if that tugging effect pulls in these two directions from the east and west, it can create a condition where these two break on either side, and this unit of land in here is sort of left stranded, right? Keep in mind, this whole body of land is floating. The North American crust is literally floating on a layer of molten magma underneath it. Okay. So if you tug and pull and break the continental landscape, it could cause this landmass in the middle to break on both sides and to drop down. Okay. Again, that's a very simplistic, probably non-geological way to explain it. But through this dropping down effect, then that creates a structure that is known as a graben. Okay. And so basically what's happening is this unit of land drops in elevation compared to the two pieces on the other side of it. Now take a look at this map here and notice that there are two grabens that are mentioned. The Mississippi Valley graben and the Rough Creek graben. Because the tugging forces of those continents being torn apart was enough to make this portion depress down and this portion drop down. And that drop down effect is what would eventually lead to what? What is now sort of in the general vicinity of the Rough Creek graben today in modern times? The Ohio River. And what's flowing through the Mississippi Valley graben? The Mississippi River, right? Now, those rivers wouldn't be there for many, many hundreds of millions to come, but eventually they will flow there. Why? Because the geologic underpinning, the foundation has been permanently disrupted because of this tugging action over 500 million years ago resulted in a graben which caused the land to fall. And then for the rest of time, unless something happens, that then is destined to become a valley, and then rivers naturally go to the lowest points of elevation. And that's makes sense to be, that's where the rivers would be. Now, I want you to also begin to look here at what else is happening. Notice all the just shearing effect that the North American coast is experiencing on the east, right? All that land is just being torn apart. But what you notice here is this sort of point down here. That's called the Alabama promontory. To me, that's not important. I don't care that you know it. But what I want you to notice is that it's because of this effect that we see the very beginnings of what will eventually become the precursor to the Gulf of Mexico, right? Imagine here you've got Florida and it does this, right? The Gulf of Mexico kind of goes around and down and up. But you see that? It comes down and around and over. This is the precursor right here that will eventually set the stage for what the Southeast will become. Here's just another way to visualize that. I encourage you to study all these various graphics and diagrams here because they really do kind of provide a lot of details. These are all from your textbook, by the way. Hopefully all of you have that. Make sure you're reading it. Okay. And so you can begin to see that formation of that very distinctive sort of notch. And later on, of course, in modern days, that sort of helps to form the southeastern coastline of America in many ways. Now, notice that the coastal plain's not here yet, right? We got to come forward in time, a few 100 million years. But this is where the land is. Eventually, this is where, which is currently ocean, is where the coastal continental shelf will be built upon and where the coastal plain will be built. So as we go forward, I want you to think of a couple things. How did the Appalachian Mountains get built? How did the Ouachita Mountains get built? How did the interior low plateaus get formed? How did the coastal plains get formed? All these are sort of the precursors to beginning to understand that process. All right, let's go forward to about 550 million years. And again, on this map, you can see where that Mississippi River Rift Valley is. Now, a rift valley sometimes will pull completely apart, as it did between these two land masses here. These are all rift valleys too. These were successful, those that separated the American continent from the others. They succeeded in pulling apart. There was a branch of that Rift Valley though that went up through here, and it started to be successful. That's why we have this notch that will eventually become the Gulf of Mexico. And if it had continued to be successful, what would it have done? It would have split Laurentia, or the American continent, into two, an eastern and western half. But instead, what it did is it failed. The tectonic processes that were leading and causing it to split stopped. And that sometimes happens, and you have a failed rift. But those processes lasted long enough to form the graben, which caused that area to drop down in elevation, which was what will allow the Mississippi River to be there for many years to come. So let's take a look at the Mississippi Valley, and we can see the impact of that drop down effect on it. Number one, here's the steep walls right here and here of the graben margin, of the graben's edge. That's what these are right here, these lines down. Okay? That's the steep walled edge of the continental crust. And then what happened is, through the many tens of millions, hundreds of millions of years, the layers of rock above it began to sag down. Okay, that's why, for example, the rocks that are currently under Nashville, as soon as you get into West Tennessee, they all begin to dive down. That's why I say that the rocks at Memphis are thousands of feet below the surface. It's because they sagged as a result of that failed rift. Now, if all the bedrock is sagged downward, and you've got these fault lines running up it, you got earthquake activity running up it, what does that mean for all the sediments that are running off the Rocky Mountains and off the Great Smoky Mountains? They're washing into it. So there's thousands of feet of dirt and sediments that are built up over top of the rock layers, all the way up to the modern level of, say, Memphis. All that sag effect is because of that failed rift there. There's one more way to look at that. Here you can see is the drop in elevation. Here's Memphis right here on the top of the Bluff Hills ecoregion, represented by the abbreviation MEM, M-E-M. You can see the Mississippi River by this little notch right there. Okay. And then look down below that, right? To get to the rock layers, the Paleozoic rocks, that's the Paleozoic era. That's Cambrian, Ordovician, Silurian, Devonian, all that stuff, all the way to the Permian. Those are the rocks that are underneath Nashville. In fact, Paleozoic rocks are the rocks right here at Clarksville. And here in Middle Tennessee, they come to the surface, even above the surface, right? They're above sea level, if sea level zero. But notice when you cross the Tennessee River, by the way, would be about right here. PCK means Pickwick, for Pickwick Dam and Pickwick Lake. We talked about that's in the Transition Hills ecoregion. So imagine if this is this line running east-west is the Mississippi-Tennessee state line. And if you're at Pickwick, you've got Paleozoic rocks at the surface. As soon as you cross Pickwick Lake into West Tennessee, you've got Cretaceous rocks at the surface, which are gravel and sand. Remember that? And then you get out to about where Jackson is. You've got the Midway Formation. You got Paleocene clay and sand at the surface. And then you go on a little bit further and you've got Eocene sands and clays and gravels at the surface. And then you finally get out here west of Jackson, Tennessee, which is about right here. You get the Mississippi alluvial plain, and this is all covered in loess and river sediments. Now, look at how far below Memphis you've got to drill down just to get to Paleozoic rock. You got to go to almost 1,000 feet. To get to the to get to the actual Grenville bedrock, you'd have to probably go another 1,000 or 2,000 feet to get to the granites that were originally laid down as part of the Grenville Formation 1.1 billion years ago. Oh, I'm sorry. Yeah, great point. 1,000 meters. So what we're looking at, roughly 3,000 feet, right? 3,000 feet below Memphis to get to the first actual bedrock. Because all this stuff is mostly gravels and sand formations and unconsolidated. Isn't that crazy? Well, it's because of the Mississippi Valley graben is part of it. Now, we've only got about 20 minutes left, or about 15 minutes actually. And I've just got a few slides, but I need you to now think with me on this point, okay? If this land over here in the Mississippi Valley is beginning to subside, or all these sediments are building up in a failed rift valley, what's going on around that? So what's happening, for example, around where Nashville is off to the east? Or what's happening up in Illinois with those land surfaces? Let's take a look at that. So this is a diagram that kind of begins to put the that failed Reelfoot Rift or Mississippi Valley Rift Zone into some kind of perspective. So here we have that. We got the Rough Creek Graben we talked about, which is the sort of coincides generally with the Ohio River Valley. And then I want you to see the Appalachian Mountains off to the east. And then you've got a few other things here, what are called arches and basins. Now, an arch is what you think it is in some respects, but it's not what you think it is in others. If somebody said to you, Chase, I want to take you out this weekend and show you a natural sandstone arch, what are they going to show you? A rock formation kind of across a gap, right? Where maybe the wind and water has eroded it all away, but you've got the sandstone natural bridge. You can go to Red River Gorge, Kentucky and see that, or various places. In this case, though, we're talking about a different kind of arch. We're talking about an arch where the bedrock has just been pushed up a little bit, where it's uplifted, okay? Nothing's eroded out from under it. It's all down there. It's just that the layers, instead of being flat, are now arched upward, okay? Now, so we have one of those naturally uplifted arches, like the Pascola Arch, across the top of the Mississippi River Valley, sort of going from northern Arkansas through southern Missouri over into Tennessee. We're going to talk about there's other arches, but these are basically areas of uplift. Then we have basins. Oh, go ahead, Ken. Yeah, very much like an anticline. These are areas that are the rock layers are uplifted. And to that same question, if the opposite of an anticline is a syncline, right? So where you have an anticline, the rock layers go up, and then always pretty much, if you have that, and I'll show this diagrammatically right here. Let me go to this one. Here's where those rock layers have been lifted up on the right to form an arch. And when they kind of connect a broad region, they're called an arch. When they happen sort of localized over, say, Tennessee and Kentucky, then that's called a geologic dome. We've talked about that a little bit so far. So this is the dome that's resulting from those rock layers being sort of pushed up. And wherever you have a dome, you can be sure that right next door, you have a syncline or a basin. Why is this important? Domes, as they get uplifted, are where the rock is being eroded from. Basins are the catchment points for that eroded rock, right? So think about if you have a mountain range. Mountain range rises. How does that mountain range get lowered? Through erosion. And where does that sediment go? It either goes out to the ocean or it goes into a depositional basin, okay? Which may or may not be in the ocean. In fact, let's take a look. Here, for example, if we go back to basins, is this large basin over what is now Illinois and Western Kentucky and Indiana. It's not a basin today. In fact, places like Western Kentucky are hilly and uplifted, but it was a basin 500 million years ago. Likewise, the Black Warrior Basin was a place where sediments were being captured and deposited. So petrogeologists, for example, want to know where these basins are because that's where there were water was standing, and that's where there was swampland. And if there was swamps there 350 million years ago, then there's that, what is going to be there today? Coal or natural gas, right? So by knowing where these basins are, you can predict where fossil fuels are located. And of course, that matters to, to our society for various reasons. So these areas like the Black Warrior Basin of Alabama is today a range of hills and low mountains outside Birmingham. But it was a basin 350 to 400 million years ago that captured all these sediments. Now, this is all going to become important, these uplifted areas and these basins, as we begin to explore kind of where the mountains were, where the oceans were, because it's all very different as you go back in time. And there's just a few of those basins there. I'm just kind of introducing these points today of these concepts of domes and basins.